Hello, I'm Kay Batwell. I'm from Electronic Design, and I'm here with Jason Landers from TrustInSoft. And today we're going to talk about static analysis, which is testing software without executing the code. So I just have to ask Jason, who is TrustInSoft?
Hi, thank you. Yeah, TrustInSoft is changing the game in static code analysis. We were founded 10 years ago by our three founders who came out of the French Nuclear Regulatory Commission and group, who were studying methods to apply formal methods around software testing, software analysis, in order to ensure the absence of undefined behaviors in mission critical code. They were working to democratize this very sophisticated means of identifying software vulnerabilities and bugs so that the general populace could take advantage in order to provide more robust devices in IoT and other critical industries like automotive, aerospace, defense, and so forth.
What is the difference between TrustInSoft's approach and typical and the typical static analyzers on the market today?
That's a great question. TrustInSoft's approach is extremely unique. The traditional static code analyzers that are out there on the market today will do what's known as semantic analysis. They'll leverage things like rules engines to look for all sorts of issues and vulnerabilities in code. Some of them very severe, some of them very minor. But one thing that they all have in common in the industry until now has been an extremely high false positive rate. They're known for providing quality detections, but they're also like needles in a haystack of other detections. TrustInSoft's approach is unique in that we're focusing specifically on undefined behavior detection, so the most critical types of issues in code, while also dramatically reducing the false positive rate through our application of formal methods, which guarantees a detection around the presence or the absence of undefined behaviors in code. And that's personally my favorite thing about it. What's different about TrustInSoft is the fact that when you run the TrustInSoft Analyzer and it says that there are no undefined behaviors detected, that's active confirmation. You know you're done, which no other tool on the market can say in quite the same way, which is tremendous value to all of our customers and a great assurance for the applications of the technology. When you're flying in a plane or driving in a car down the road, you will appreciate the fact that it's been tested with technology like TrustInSoft, which is guaranteed that there are no possibilities of buffer overflows or hackers taking over vehicles and things like that. It's robustness that so far has been exclusively reserved for governments and those with an extreme amount of resources and PhDs on staff. TrustInSoft has packaged that expertise into our analyzer and is now bringing it out for everyone.
I would love to see a demo of this in operation.
Yeah, I'd love to show you. Do you see my screen okay?
Oh yeah.
All right, so very quick and simple demo here. This is representative of how we often will encounter a customer who is doing things the traditional way, and they're interested in working the TrustInSoft Analyzer into their workflow and also seeing what it can do for them. So what I have here is just a very simple little function called increment array. It takes as its input an array of integers, and the length of that array. It loops through each element and it increments them by one. Pretty simple. We also have a test driver, and this is representative of how many customers today have some set of tests that they're running against their code. And so we have traditionally here a test of a small array, a handful of discrete values, a large array test, so 1,000 randomized integers. And then we'll test some corner cases also. We'll test the zero length possibility and then the null array, or the possibility that the array is uninitialized. And many customers are doing things like this, where we'll say, look, let's run our tests. Still no TrustInSoft Analyzer involved at this point. If I scroll back up a little ways, things are looking pretty good. Are my four tests, each of them ran. You can see the before and afters. Each of those integers was incremented. All tests are passing. And by the way, extra bonus, all of our lines of code in that function were executed. So we have 100% code coverage. This is looking pretty good to me. However, there are issues lurking within this little function here. And so now enter TrustInSoft, how to get started. For many customers who are in this situation with existing tests, for instance, they can just literally run them as they are through the level one of the TrustInSoft Analyzer, which will apply its own assertions and look for issues even while it interprets the other existing tests that are there. And so you'll notice even in our CLI output here, some issues have been found. The analyzer also will produce a report, which you'll see pop up at the end of the run here. And the report will give us a greater amount of detail as to what exactly the issue is here. We're just finishing our tests. You can see clearly in that CLI output there, 2 undefined behaviors were found. And there's a quick summary on the title page of the report. Actually, the issues are the same issue. We hit it twice because of the small array and the large array tests that were there. The problem is, as you can see here, we're reading one past the length of the array. And you can see the assertion down here that shows that. And as I look back up at the highlighted line of code where there's this issue, I can see right above that, the problem is we have this greater than or equal right here, which should actually just have been a greater than 0. Because otherwise we're reading one past the length of the array, and this was silently failing in the test that we were previously running. So of course our goal is to eliminate undefined behaviors. And so let me just come here and make that quick change and see if we can get a clean result. So all I did was delete that equal sign. Now the function says greater than 0, and we'll rerun that level 1 analysis that you just saw me do in order to see if we can produce a clean result at this point to ensure, to guarantee the absence of undefined behaviors. But there's a big asterisk when I say that, and that is the presence or the absence of undefined behaviors at level 1 in the analyzer is linked to those discrete input values that you saw being leveraged in those individual tests. So when the report here pops up in a second and it tells us that there are no undefined behaviors, that means there are no undefined behaviors for those series of integers that were used in those 2 tests, leaving open the possibility that for other types of inputs or other values, there could potentially be undefined behaviors still lurking in our code, which is why we say, although it is so easy to get started with the analyzer and just rerun your existing tests like you saw me do here, this, by the way, is mathematical guarantee of the absence of undefined behaviors for those specific values. But we want to do even better than that, right? We want to say for any possible value. It's not acceptable for any of our customers to say merely just for those specific values. So what I'm going to do next is I'm going to run the analyzer at level 2, which is going to run the same 4 tests, and those tests will pass because we've already mathematically guaranteed that they're sound. But it's going to invoke a 5th test, which is a generalized array, test generalized array, and you can see it here as this function. When I invoke the analyzer at level 2, it will run. It initializes an array of integers, 1,000 elements long, and then it takes advantage of a function here called tist_make_unknown, which is our input generalization technology. There are many helper functions that TrustInSoft provides, and those functions allow you to do things like this, to write fewer tests while increasing the coverage. So we will test all possible integer values up to 1,000 integers long. And you can see in the comments here some of the math behind exactly how many inputs that represents, which is a large part of what I was saying earlier. You would never spend the time to incrementally do this one at a time, let's say. But I can just invoke this to say make tis L2, and we will run the generalized inputs analysis to see if there is additional undefined behaviors for any input values. And in fact, as you can see there on the CLI output, there is one more undefined behavior. Notice also how fast that was. That took about the same amount of time as it took to run the level 1 analysis. However, we tested all possible integer values up to those 1,000 integers long through this function, and we uncovered one more pretty significant issue, and that is there's an integer overflow present here. When we loop through all the elements of this array, there's no protection in this function against the possibility that the integer will already be at the int max for this architecture. And so when we blindly go and try to increment that value, we've just created ourselves an integer overflow. Before I go and I fix this, I also wanted to just show you real quickly the fact that there is a powerful interface behind the TrustInSoft Analyzer as well. Everything you've seen so far as being CLI driven, CLI output, the HTML report that gets generated out of JSON outputs and things like that. But there is also a sophisticated UI that many of our customers come to depend on when it comes to trying to identify complex issues, complex call chains. You know, for instance, in the demo, we're just looking at one tiny function and all the issues are self-contained. But in production code, when we see things like integers or divisions by 0 and things like that, the source of that issue is often hundreds of thousands of lines away in the code from where it actually manifests itself. And in scenarios like that, where this interface comes in extremely handy. It shows you your code on the right, the analyzer's view of that code in the center, with the issue highlighted in bright red here, the signed integer overflow. But this allows you to step through all of the call chain, look at all of the values every step of the way, and to really understand in a thorough level of detail what is the issue so that you can more quickly fix the issue. So we're not purely just about issue detection. We'll also help guide an engineer to help assist them to understand and fix what the problem is. And so just to round this out, of course, the solution would be to say, hey, if my value is less than the int max for my architecture, then increment that function. And if I rerun my level 2 analysis now with that last fix in place, we should be able to achieve a result now that mathematically guarantees the absence of undefined behaviors for my function. And indeed, that is what we have. And so it is just that simple to iteratively run the analyzer at level 1 or level 2 and leverage our built-in helper functions to generalize your inputs and to achieve this broad test coverage in a tiny fraction of the time that would otherwise take you to brute force it or to individually write that many unit tests.